Welcome to lesson 6.4 on the power law of logarithms. Suppose you invested $100 in an account that pays 5% interest compounded annually. The amount in dollars in the account after any given time, which we'll measure using the variable t in years, would then be given by A equals 100, which is your original investment, times 5% to the power of t. Now suppose you wanted to know after how long a period of time, after how many years, the amount in the account was a certain value. Well, we can do that, but it's a little bit tricky because the exponent here, time, the variable time is in the exponent. So what we would need to do is use logarithmic form for this equation. Logarithms are very useful for solving an unknown exponent in an equation. So consider this equation. We want to find the time after which the value has doubled. So we're going to substitute $200 for A, because the amount that I invested was $100, but I want to see how long it takes to double. And it's going to be compounded annually at 5%. And I can go ahead and solve this using logarithms. My first step is going to be divide both sides by 100. 200 divided by 100 is 2. And 100 divided by this whole side divided by 100 is just canceling out the 100 here. So we're left with 2 equals 1.05 to the power of t. Well, now we're left with something that looks fairly familiar. We want to find the value y, the exponent y, to which we have to raise the base b in order to come up with the value x. So let's write this in logarithmic form in order to solve. Scroll up. T, therefore, is equal to the log of 2 to the base 1.05. So I have my equation for finding t, but it's a logarithmic equation. And my calculator can't solve this logarithmic equation with a base of 1.05. It is only able to do common logarithms and the natural logarithm, which we haven't talked about yet. So how am I going to figure out at what point in time t my investment value has doubled? Well, we'll look more closely at that in investigation 2, and we'll come back and solve this problem. In investigation 2, we are trying to discover the power law for logs. So I have here a list of logarithms, and you might notice they are all with the base of 10. So when we're working with the base of 10, I don't need to write in the base here, 10. Don't need it. And you might notice also the relationship between my x values here, 2, 4, 8, 16. So I'm just going to plug these into my calculator, organize them as such, and we're going to be looking for a pattern where we want to find out how all these values are related to the log of 2. So log 2 in your calculator, approximately 0.301. We'll go to 3 decimal places. All right, log of 4, 0.602. Well, finding a pattern in this one is going to be fairly straightforward. Log of 8, 0.903. Log of 16, 1.204. Now, we can see a clear pattern. I'm seeing that each time my value is simply adding the log of 2 to the next, to get the next value, to get the next value, to get the next value. So I can make a prediction about what might happen at log of 32. Well, I think I'm going to be adding 0.301 to 1.204 and be left with 1.505. Go ahead and check that in your calculator. Yep. But what we want to do is find a general equation for the log of 2 to the power of n, any exponent of 2. Well, down here we have this 2 to the power of n, so it might be helpful if we just go ahead and insert our exponents here. 2 to the power, this one is the same as saying the log of 2 to the power of 1. Here we have the log of 2 to the power of 2. Log of 2 to the power of 3. The log of 2 to the power of 4. And I hope that now we can see the connection a little bit more easily. All we've really done here is taken the log of 2 and we've multiplied it by 1. To get 0.602, we have the log of 2 to the power of 2, but all we've really done is taken the log of 2 and multiplied it by 2. To get to the log of 8, we've taken the log of 2 and multiplied it by 3. 3 times 0.301 will be 0.903. To get from here to here, we're multiplying by 3. Log of 16. We've really just taken the log of 2 and multiplied it by 4. We can see that right here. So, in general, to find the log of 2 to the power of n, it's going to be equal to n times the log of 2. Well, that's good to know that we can use this approach when we have a logarithm of 2 to the power of n, but what about all the other options? What we're going to do now is prove the rule that we just investigated using algebraic reasoning, and then we'll rewrite it as a rule that you can apply to any numbers, any logarithms. So let's start. We're going to let w equal the logarithm of x to the base b. Okay, so we've got w, which equals the log of x to the base b. We're going to write the equation in exponential form. So what this is saying is w is the exponent that I need to raise b to in order to get the value x. So in exponent form, we have x equals b to the power of w. I'd like to raise both sides to the power of n now. So we're going to be left with x to the power of n. I need to do the same on both sides. We have b to the power of w to the power of n. Now I can apply the power law of exponents that I used last lesson. So x to the power of n equals b to the power of w times n. Well, let's rewrite this again in exponential form. Sorry, logarithmic form. We're going to have the log of x times n. Sorry, the log of x to the power of n, some base b, is equal to wn. So wn is the exponent that I need to raise my base to in order to come up with the value x to the power of n. That's exactly what we have here. Wn is the exponent that I need to raise the base to in order to equal the value x to the power of n. Well, let's substitute w equals log of b x to eliminate the w, okay? So on this side, we still have the log of x to the power of n to the base b, and we said w is equal to the log of x to the base b. So now on this side, we simply have n times the log of x to the base b. As an official law, we have the logarithm of x to the power of n to any base b is equal to n times the log of x to the base b. And this is true. I'm going to go to the next line here. Wherever b is greater than 0 and b cannot equal 1. But also a new restriction that's different from the exponents. X cannot equal 0. Maybe I'll write that in the next line, otherwise I'm going to run out of space here. X is greater than 0, and n must be a real number. Alright, so we have our power law for logarithms, and we're going to try a few examples. This is example 1 on page 343, and in example 1a, we are asked to evaluate the log of 9 to the power of 4 to the base 3. Okay, I'm going to rewrite this because I think I have a connection here between this 3 and this 9. So we can rewrite this as the log with a base of 3 still. And I'm going to rewrite 9 as 3 to the power of 2 times 4. And hopefully we can start to see a connection between the proof that we just finished and this example. So by my law of exponents, I have the log still base 3, and this is, I'm just going to, because of the power of powers rule, I'm going to multiply my exponents. So I have a value here of 3 to the power of 8. So what I really need to find here is what exponent do I need to raise 3 to result in the value 3 to the power of 8. And that answer, of course, is 8. If I raise 3 to the power of 8, I will get the result 3 to the power of 8. This is the same example again with a different method. You may have noticed that in the last working through of the example, we used the power law of exponents, but we never actually used the power law of logarithms. So let's see what happens if we actually apply the power law of logarithms. This log of 9 to the power of 4 with a base of 3 becomes 4 times the log of 9 to the base 3. And we can apply some of the same things we did before. This is 4 times the log of 3 to the power of 2 base 3. This whole guy simply turns into 2 because that's the exponent that I would need to raise the base 3 to result in 3 to the power of 2. So here we simply have 4 times 2, which equals 8. And hopefully you could see this calculation was a little bit less tedious than method 1. Okay, let's do a few more examples applying the power law of logarithms. Here we go, we have the log of 8 to the power of 5 to the base 2. This is equal to 5 times the log of 8 to the base 2. And we can see here that 8 can be expressed as 2 to the power of 3, which means this whole side is simply equal to 3, which equals 15. Example C, the log of 0.001 squared. And we know that since the base is not identified, it is a base 10. So what we have here, according to the power law of logarithms, is 2 times the log of 0.001. Well, 0.001 is simply 10 to the power of negative 3. Now I have my little base, my imaginary 10 here. And I know that this whole thing is going to reduce to negative 3. 2 times negative 3, which equals negative 6. So the log of 0.001 squared is negative 6. Okay, a trickier one here. The log of the square root of 125 to the base 5. Again, we're just going to apply our power law of logarithms. The first thing I need to do then is express this square root as an exponent. Well, the square root is the same as raising 125 to the power of 1/2. So bring that 1/2 out in front according to the power law of logarithms, leaving us with the log of 125 to the base 5. And this little piece is simply saying, what do I need to raise 5 to result in 125? Well, little side work over here, 5 times 5 is 25. 25 times 5 is 125. So I need to raise 5 to the power of 3. So 1/2 times 3, which is 3/2, is equivalent to the log of the square root of 125 to the base 5. Okay, let's apply our skills back to the example that we saw in investigation 1, where we had an investment of $100 and we wanted to find the amount of time it would take to the nearest year for that investment to double, for the $100 investment to become $200. And we already did the first step of this. We divided both sides by 100, so we're left with 2 equals 1.05 to the power of t. And we said that that t as an exponent is a little bit troublesome. But now we have some rules and some strategies for bringing that t down from the position of an exponent using our rules for logarithms. So what I want to do here is I want to take the log, the common log of base 10, of both sides. So it's all good as long as I do the same thing to both sides. If I take the log of 2 and the log of 1.05 to the power of t, then I've done the same thing to both sides of my equation. All right, next step is applying the power law of logarithms to the right side. So we have log of 2 here on the left, but now we have t times the log of 1.05 on the right. Well, let's divide both sides by log of 1.05 in order to get t by itself. T equals the log of 2 divided by the log of 1.05. And I can put that in my calculator and I will come out with the result that t is approximately 14.2. And so it will take approximately 14.2 years for the initial investment to double in value at a rate of 5% interest. The technique that we used to calculate the number of years it would take for our investment to double in value can be applied to logarithms of any base. And it's called the change of base formula. Let's explain before we write it officially on the bottom. So we're going to let x equal the log of m to the base b. Okay? So x equals the log of m to the base b. If I want to write this in exponent form, all I'm saying is that b to the power of x equals m. Now I can take the common log of both sides, so the log of b to the power of x is equal to the log of m. And according to my rule for logarithms, this left side becomes x times the log of b, and the right side remains log of m. Now I can divide both sides by log of b in order to determine my x, log m over log of b. So the change of base formula is as follows. For any log of m to the base b, it will equal the log of m over the log of b. In order for this to work, m must be greater than 0, b must be greater than 0, and b cannot equal 1. Oh, I'm off the page here and I can't get it on. There you go. The log of m to the base b is equal to the log of m over log b, where m is greater than 0, b is greater than 0, and b cannot equal 1. Okay, in example 3, we'll be applying this change of base formula. So I've written it at the top of my page so I can keep it in mind. And a gives us the log of 17 to the base of 5. And according to the change of base formula, this will be equal to the log of 17 over the log of 5. Punch that into my calculator, giving the result approximately, this is equal to 1.760 to 3 decimal places. Good. We'll continue on in b. b gives us the log of 10 to the base of 1/2. Again, equal to the log of 10 over the log of 1/2, or 0.5. And we can put that in our calculator. The log of 10 just reduces to 1, remember, because the base is 10. So what exponent do I need to take my base 10 and give it the value 10? Well, 10 to the power of 1 will be 10. So I simply have 1 over the log of 1/2, which is approximately equal to negative 3.322 to 3 decimal places. Okay, example 4 asks us to graph the function log of x to the base 5. And there are 2 methods for this one. Number 1 is going to be to graph the inverse of this, which is an exponential function. So the inverse function of f of x here, we'll call f inverse of x, is 5 to the power of x. It's simply the exponent form of this guy right here. Okay, so now we're going to graph that and then reflect it over the line y equals x. So we'll draw our inverse function in blue, and we'll leave red for the actual logarithmic function. So here we go. F of x equals 5 to the power of x. Well, it's going to cross the y-axis here at 1, and it's also going to meet at, by the time we have an exponent of 1, we're going to be at 1, 2, 3, 4, 5. Y equals 5. So this is going to come across like this. It's going to start bending up, and it's going to come up. There. That is the exponential graph, 5 to the power of x. And all I need to do now is to graph its inverse. Well, we learned earlier that the inverse is going to do some of the similar things, except instead of crossing the y-axis at 1, it's going to be crossing the x-axis at 1. Instead of reaching the point 1, 5, it's going to be reaching the point 5, 1. All the coordinates are simply flipped, right? The x and the y values have swapped positions. So 1, 2, 3, 4, 5, 5, 1. This is going to come up. It's going to stay greater. The domain is x greater than 0. It's going to cross here and bend over. And there we have sketched the graph. F of x equals the log of x to the base 5. Method number 2, I can do on this page as well. Basically what we're going to do, we have this log, and then we take the change of base formula, which we just finished doing examples on. And so we have f of x is equal to the log of x to the base of 5. Therefore, it is equal to the log of x over the log of 5. And you go ahead and put that in your graphing calculator or GSP, and it will give you the same red curve that we have here. So that's method 2, put in your graphing calculator. That's my preferred method. All right, homework for 6.4 is from page 347, numbers 1 through 10. Enjoy.